Thank you. And good morning, everyone. I am Vikas from Indian Institute of Technology, Jodhpur, India. I shall be presenting on IoT-Enabled hBN AlGaN GaN high electron mobility transistor for carbon dioxide monitoring. So to start with, carbon dioxide level is critical in various domains, be it environmental surveillance, industrial processes, space applications, or specifically if we are talking about confined spaces like we have in spaceships and these things. So my primary work is to do carbon dioxide monitoring for confined spaces where the carbon dioxide level can go up as well as lower carbon dioxide levels can be reached. And that also in like most of the sensors, okay, I will be discussing that. CO2 has significant industrial and environmental concern. Any prolonged exposure to high level of CO2 can cause health issues as well as contribute to global climate change. Hence, accurate CO2 detection is quite important. So conventionally, it has mostly been done using either metal oxide semiconductor-based sensors, but these MOS-based semiconductor face a problem that they have poor selectivity as well as high temperature is needed for sensing. Added to that, they have lower stability and sensitivity drift is there over time. As well as controlled fabrication of these devices is a very limiting factor. So the possible solution some people have worked is ISFET, silicon ISFET based sensors. So it is simply based on having like, on white it's now. So if we talk about metal oxide semiconductor, it works on the principle that between two electrodes there is metal oxide. So due to the interaction of the gas and the metal oxide, the resistance of this layer changes and that leads to the change in current. So we are able to detect that. When we come to ISFET based sensors, there it is having the transistor which has channel, source, drain, as well as gate. So here we need an extra bias, that is on the gate, a reference electrode is needed to switch on the device. And on the gate region, the changes that happens, that the adsorption of the gas molecule on the material actually leads to a formation of a surface potential that adds to the gate voltage. But this again have the problem that it has weak selectivity, as well as it needs a reference bias to keep the device active. So it has excess gate power dissipation and sensitivity drift over time and lower signal to noise ratio. So our solution is to overcome these problems using AlGaN GaN HAMT. So it is simply a junction between two different semiconductor materials, that is the heterojunction that is working as the channel. So these two semiconductor having two different band gaps and a 2D electron gas is formed at the interface between the undoped GaN and the AlGaN layer. So if you see between the AlGaN and GaN, at the interface, a surface like a sheet of charge forms. As well as we are passivating this, all the surface except for the gate area so that we alleviate the surface trap-related degradation mechanism and ensure that there is no surface conduction taking place. Just like the ISFET, all the conduction is, all the principle that is working is due to the interaction of the functionalized layer and the gas. So it is based on a voltage, like surface potential that is forming, that will lead to the detection. So the advantage with this, specifically the 3 nitride materials like the AlGaN, GaN, and these family, uh, it has wider band gap, so it has better thermal and chemical stability. So we can use it for a wide variety of uses, specifically in all the, like all kind of environment, even if it is corrosive and this kind of environment. Plus, they have the spontaneous and piezoelectric polarization that leads to the formation of the 2D electron gas that acts as the channel. So the question comes, why to go for this? Why HAMT? So if we see a normal IS-FET kind of structure, so it is like if the electrons, like it is like a high-speed car moving along with low-speed cars. So at the end, and that also in haphazard manner, that will actually lead to reduction in speed. And that is what happens in case of a bulk material, where scattering happens. Whereas, if there is a LAN in which all the cars are moving in the, with the same speed, the same thing will be much faster. That happens in case of a 2D electron gas, where since the carriers are confined and all can move in one, like a one LAN, single speed highway, that leads to better sensitivity, as well as any changes on the surface is easily reflected in this flow. So how this 2D electron gas forms? So due to the spontaneous polarization of the AlGaN material, the electrons from the top surface move towards the interface, and due to band bending and aligning, we see that at the interface of AlGaN and GaN, charge trap, and in this trap, like we have abundant electrons coming here that can move only in X and Y direction. If we, like this one is the top, and if we go bottom, so at the interface, they can just move along the interface, not up, not down. So the sensing mechanism is like on the gate area, if we put some functionalization material. So first, there will be a current between source and drain. That is the base current we have. And once some gas molecule comes and interact with our surface functionalization, there the current will change due to the potential that is forming, just like we are giving some gate bias or gate voltage to it, small gate bias, and that leads to change in the current. And this current change, that is delta I, that we are taking as our change, like that we are taking as the response. So how we fabricated this sensor? So we started with first the epitaxy growth of these structures. So after that, we started with the metal deposition over the wafer. So on top of this AlGaN-GaN interface where 2D electron gas is already formed, we are depositing aluminum, chromium, gold over it, and then using mask aligner and lithography, we are patterning, and then we are, once the pattern is done, this sensor is made, we are doing rapid thermal annealing. So what it does is that, if you see on the right side, the source and drain, that patterns we have made, they are on the surface. So we are annealing this whole thing at 870 degree for 45 to 50 seconds. That leads to the source and drain to diffuse up to 2D electron gas that is located around 18 to 20 nanometer below the surface. And as such, before, if we check, the current is very less, like it is actually almost open. When we do the RTA, after that, we see a proper transistor-like current. So just to verify, in some of the devices, we first even made a gate and checked with different gate biases. It is giving a transistor-like characteristics. But for our work, we just went with this source and drain, and we passivated all the area using silicon nitride, like deposited it, patterned it, And then in the gate area that you see in the central part, that we are using for functionalization. We are functionalizing hexagonal boron nitride for using Scotch tape method on the gate surface. We are even confirming the Raman and seeing the AFM, took the AFM of it, and the thickness that we are getting, it is not very thin like we expected, but yet it is in the range of around 200 nanometers. So then testing it for carbon dioxide, we started with 1 ppm, going up to 100 ppm. And for different gas concentrations, the response is changing, and we are getting appreciable response even for 1 ppm, say like around 18% response for 1 ppm, going up to like 56% for 100 ppm. If we check, we even check the selectivity, and it is having good selectivity towards CO2 compared to NO2, CO, ammonia, oxygen, and hydrogen. As well as we check the repeatability, and the greatest advantage that we are getting here is that we are not applying any temperature here. All this is at room temperature. So most of the sensors that are at present being made or used, they need some temperature to be given. First, we are removing the reference bias, no need of reference bias. Plus, second, we are removing the need of any kind of heater or heating element. So, and then we tested even an IoT integration of this sensor. So we simply made a voltage divider circuit for this AlGaN HEMT with a resistance on the top. So using the voltage divider, we are getting some potential over it, which we are fitting into our 12-bit ADC. And it has Wi-Fi and Bluetooth, which we are using for transmission to our app, mobile app. Along with this, we have one part that we have added is that we have added a humidity and temperature sensor along with this, so that we can monitor temperature and humidity, and we can work over it in future, where we are able to reference all these values along with the referenced humidity and temperature. So like these are mostly taken at 25 degrees Celsius. So if we can have a range of temperatures, say going from 18 or 15 degrees, going up to 80 degrees, we can have a range of different temperatures as well as different humidities, so that we can feed and we can have a. So in conclusion, we made a sensor which has sensitivity of 56% at 100 ppm. And the greatest advantage we are getting is a room temperature operation. And we are able to even do an IoT integration of it. Compared with some of the sensors that has been reported earlier, we are having a bit higher response time, a bit higher recovery time, but the operating temperature is drastically reduced from 200, 250, 300, like that, to room temperature. So the potential improvements that we are at present working along with it is the further reduction of hBN thickness for better sensitivity, since we got only up to 200 nanometer, and reduce recovery time by introducing some other nanomaterials like layers or particles over it, and improve selectivity by multi-layer functionalization, and also to go for higher concentration responses and check the humidity and temperature variation. So that's all with my presentation. I would like to acknowledge my group, Nanosensors Research Group at IIT Jodhpur under Professor Mahesh Kumar, and Prime Minister Research Fellowship from MOE India. Thank you.